But I like October and like I basically told them about how it's
All right, cool. Can somebody give me a thumbs up if you can hear me? If the audio is working okay? We're just, all right, thanks, Nikhil. Great. All right. There we go. No point.
Just like
Okay, let's go back here. All right. When I go down here, laser. It's a laser. All right.
also you there. So you can
And I get the laser. I think it's
these are better. What is that? Oh no. When I first created the matrix, there was very big. It is like a mean to make the matrix of all the then it's like the way up to the center of the matrix. The thing is they say it's a 23 by 23 matrix. But X not and Y not are so higher than that. 23 by 23 matrix doesn't have like yeah, I just like drag around and but then it's supposed to be the center of the part. I guess it's 23 by 23 by 12.
all right. And we'll get started. Any questions from Monday's lecture that are lingering that you need to address before we get started here? A number of people asked, what's the, as we're launching into this part of the course, what's the requirement in terms of mathematical background to be able to do things in the course? And over the next two lectures, I think you'll see what that is. Okay, so if you're wondering, like how much math do I need to know? I think by the end of this lecture and the next lecture, you will know whether or not this is math that you're comfortable with and that you know. And if not, you can try and catch up with that math. Tom's going to run some really helpful extracurricular activities on Fridays to look at the Fourier transform and things like that. And we can give you other texts, or you can become an observer if you want, if you don't want to try and undertake all this stuff. So we'll start here. This is where we finished last on Monday. Okay, there we go. And we were talking about the impulse response function, also known as the point spread function, for our imaging system. Recall the model that we've got running here is we have some input. In this case, we're going to take a very small dot input or some very small signal for CT, ballpoint pen, ballpoint, that little sphere. For MR, you can make a very small sphere of water. They used to have spherical vitamin E capsules that we used to use for point spread function or for small objects for labeling things. And in MR, those small things are usually bigger than you use in CT. Anyway, this is our input. We're going to call this a delta function. And we can shift the position of the delta function to test what our system does when we shift the input, just by expressing it as follows, where we have a psi and eta, which is a displacement from the origin. Okay, and then we can encode that as these subscripts. So if it turns out that when we shift our signal from the origin, we are required to have a new point spread function or a new impulse function for every value of psi and eta, for every offset, then it is not a shift invariant system. It has a whole set of point spread functions that you need. It could have a functional dependence, for these functions, but if it is shift invariant, this thing is independent of the offset in psi and eta. So what we're going to do is characterize our system with this impulse response function, such that when I put a delta function into my system, I can measure that impulse response function. And the way it works, the way the impulse response function works is if I have something I'm trying to make a picture of, which is a function f of xy, in this case, it's psi and eta. So it's a 2D function. And that could be a picture of somebody's face. It could be a blob. It could be a brain and a slice. It's a two-dimensional function. Then the way I create the image of that function as a function of space is I multiply the function by the point spread function at each point xy, right? And then integrate over the whole field, right? So I have my object, right? I multiply by the point spread function, integrate over the whole field, and whatever number, I get a single scalar number, let's say, whatever that number is, that is the value of my image at gxy. Okay, so it's actually taking information from the entire field of view to make a single pixel, right? And the relationship between that single pixel and everything around it is governed by this function. So you can imagine if this function, the point spread function, is a really narrow thing like a delta function, you're in good shape, right? If it's a delta function, then gxy is just going to be a replicant of what your object is, right? If it isn't a delta function, if it's something wider than a delta function, so, has width or a blob, then your object gets blurred to become the picture. That's the most common thing that happens, okay? So, and this is the characterization of our imaging system. It's the point spread function or the impulse response function. So if we assume, or if we can cut down our field of view or our analysis to a smaller region, such that the physics of the situation tells us that the point spread function does not change with a function of position, then I can make a point spread function that is really only dependent on two variables, right? X and Y, right? So it's one point spread function, and as I move away from its center, it's the same function regardless of where it happens in the field of view. And therefore, I really only have two free parameters here, as opposed to 4 up here. And so this is a shift invariant system, right? So it's actually a nice property to have for an imaging system. Most imaging systems, when you look at the really precise details, are not shift invariant, right? There's some kind of change as you move away from the central area that's really well sampled or whatever, but it's an assumption that's made a lot in doing analysis of signal to noise and imaging systems. So let's go back and look at this integral once again. Now that we have a point spread function that really is only dependent on two variables or two free variables, this first argument and second argument, right? When I put that in and perform the same multiplication of my true object with the point spread function, and I integrate over the whole field of view, this is the new integral I have. This is also the definition of what's called a convolution. And when I have this shift invariant point spread function, I can express my change from my real object to my image as a convolution of the real object with the point spread function. So that's a huge deal, actually, because this is something that's very simple, right? It's mathematically, it's known. It happens a lot in a lot of fields. And we'll see it has a special relationship to the Fourier transform, the convolution does. So when I'm shift invariant, I can say that, look, to get my picture, all I'm going to do is convolve my actual object with my point spread function, and then I got my picture, right? And so what does convolution look like graphically? If I have two functions, here's f is one function. It's just one of these rect functions, and this is a single ramp function. I say, what does f convolved with g look like? In performing this, went too far. This integral here, we can do it graphically. So the first thing we do is we flip g, because there's a negative sign in, let me see, right here, these negative signs. So we have to flip g around to here. We then multiply that flipped g times f for a specific offset in g, because we're gonna integrate across. This is just one dimension. We're gonna integrate from -infinity to infinity. And when g does not overlap with f, we get a 0, right? When g, if we shift this way, overlaps with f such that the product of the two is, because this is 1, this is the product of the two, this area, we plot that area. And then here, when g is shifted such that they're kind of aligned at 0, the product of the two is this area. And then as g keeps moving, the product of the two becomes a smaller overlap area. So I start with a rectangle function. When I convolve that function with g, I have this kind of, charge up, decay down function, right? Which it looks kind of like both of them, right? So In the same way, you can convolve G with F and you get the same function. So in that integral, it doesn't really matter who goes first, right? So if you just look at the equation with the integral, if I put the F over here, it doesn't matter. So the convolution is, symmetric, or you can do G convolved F is F convolved G. Convolution is used a lot these days, particularly in convolution neural networks, right? So in these fantastic algorithms that remarkably pick out your relatives out of photographs and put them in buckets on your phone, at all ages, which I still haven't figured out how they do this. Like, it picks out my daughter. She's, 33, and it picks her out when she's 2 and stuff like, and labels her all the way down. It's kind of spooky, right? That these algorithms are so good at looking and saying, no, that girl is the same as this 33-year-old, right? And so these algorithms use convolution neural nets. They train networks to look at these photographs, run convolution kernels, many convolution kernels over them, add up those solutions to those, and that with certain weights, certain coefficients, and then do it again. And you downsample, do it at a blurrier picture, get a whole bunch of new coefficients, downsample, do a blurrier picture, get a whole bunch of new coefficients. And they're all convolutions all the way down, right? And then it all sums up and says, oh yeah, this person is that person from the picture. It's pretty spooky. And now, when you travel, you walk up to the thing at customs, and I was shocked the first time it happened. I think this happened 3 years ago or something like that. And I just walked up and it said, well, hello, Elliot McVeigh, your, gold thing has expired, right? And I looked at it, I hadn't given it a note, hadn't put a thumbprint, I hadn't done anything. I just walked up to the machine and it told me that my gold global entry or whatever is expired. And I was like, oh, I don't like that, actually, So you can imagine everywhere you walk in the modern world, virtually, and many countries will just have this all over. You are being tagged, right, and spotted, because these algorithms are so good. So anyway, at the core of these algorithms, sorry about that aside, is our convolutions. And what happens is you have a function. This is, say, our G function, right? And this is our image F, and you multiply G times place on F, however big G is, and you raster across the image, and then you get a number at each point where this is located, right? And so that's a 2D convolution. It'll just raster across this whole image. So that produces a new image, right? And this convolution function looks like it's taking a derivative, right? It has negatives here, zeros here, and positives here. So if there's a big slope here, it's going to come up with a high number and say that's a big slope, at that point. If it's constant, this will all integrate to 0 and say there is no slope in this little patch right here. So that's what this is doing. And these convolution filters, normally there's like 64 of them or something, or run across a picture to figure out what the picture's doing. So convolution, important thing to know, right, about what's going on with convolution these days. Separable systems, turns out if you can characterize your point spread function by a blurring in X multiplied by an independent blurring in Y, that is, you don't need to know what X you're on in order to execute your blurring in Y, then you have what's called a separable system, right? Whatever row you're in, you're going to blur the same in Y, right? Whatever column you're in, you're going to blur the same in X. And so that makes the mathematics somewhat simpler, right? Because these convolutions turn out to be 1D convolutions as opposed to a 2D convolution. And they don't go up linearly with D, right? So if you have a large convolution kernel in 2D, it's more expensive than these 1D kernels that are multiplied together. This was an issue when I was a grad student because we had, what the heck were those called? The arrays, Tom? They did 1D convolutions and 1D Fourier transforms really quickly. Array was in the title of that device, right, Tom? What the heck was it? Yeah, but anyway, used to buy these things. They were like graphics cards, but not really. They were just like floating point arithmetic cards. But 1D, they could fly. 2D, not so much, right? So this is much more efficient in terms of doing the processing of the picture. So let's look at the result of 1D convolutions on an example picture. And so this is a really nice MR picture of a brain. This is probably from 30 years ago. This is what you would get. I used to have these in my wallet when I first got into MR in the mid 80s. We had a scanner, and back then, if you're a grad student, anybody could just jump in the scanner anytime and just scan whatever the heck you want. And there's no IRBs or anything like that. So just jump in the scanner and make one of these sagittal pictures of your own brain. That was great at like parties and things like that. I go, yeah, this is my brain. It's all there. It's like, and use it for interviews, things like that. And they most of them look like this. You're pretty indistinguishable. The interesting thing about head MR though is that when you go to say de-identify a head MR and it's a volume study, can you de-identify it? Like get rid of all the information in the header and say, okay, now I've that's an anonymous data set. Is it anonymous? It is absolutely not, because you can do a 3D reconstruction and look at that person's face, right? So you just do a 3D reconstruction and there they are staring at you. Usually they have their eyes closed because they've been in a scanner sleeping. So it's a bit of a trick, right? How are you going to give the public, say, de-identified MRI cases when you can look at everybody's face? Luckily, I work in the heart, and yeah, nobody can see inside there. So unless you have some weird object on your chest, right, then you could recover who that is. So anyway, be careful of that. Some people get caught with that problem. But what we're going to look at is convolving this image with a point spread function. I'm sorry. Oops. Where the heck did it go? Oh, I jumped way ahead. Okay. Anyway, we're gonna go forward then back. With a 1D convolution in this direction in X. So this is X in this direction. This is Y. Most MR scans from this vintage, this dimension would be 256 pixels, 256 point estimates. This would be 256. Nowadays, it's probably 512. Tom can tell me if it's up to 1024 these days. But when we convolve this function, without paying attention to what column we're in, we don't change the convolution kernel, we just convolve in X this way. This is the image that comes out. Okay. And you can see it's blurrier, but principally, if you look at this edge here compared to here, this got really blurry, right? This really thin white line here is now completely blurred out. Right? On the top here, if I do a profile this way and ask what's the spatial resolution or the sharpness in Y as I move along in Y, it's still pretty sharp, right? Because I haven't blurred it, right, in the Y direction yet. I've only blurred it in this direction. Right? Then if I do a convolution of this function or this image with my point spread function in Y, now this edge here gets blurred, right? And so that's a separable system. We blurred in X, and then we can blur in Y. And the Fourier transform also is a really nice function for computation, because if you're doing a two-dimensional Fourier transform, you can just do it all in X, and you have a picture after that, then do it all in Y, and then you have your final picture. Right? Okay, so I think that's separable. Okay, we got to here. What we didn't do is this. I think I skipped right over it. Okay. If you have two processes inside your imaging system that have different point spread functions, right? So let's say this is maybe a lens number 1, and then that focuses down to lens number 2, and there's some point spread function associated with going through there. You can do them if they are shift invariant and they're linear shift invariant system. You can do them in the opposite direction, or do the H2 first and then H1, and you will get the same output. Okay. In fact, you can convolve this function with this function to get a final function that you convolve with F to get G. So those are all equivalent. Okay. If it's a linear shift invariant system and your final image is a composite of one process through this subsystem, another process done in parallel with this subsystem, and it's the sum of these two that make the picture, then you can just add up those two functions and do the convolution, right? So that's as if it's a linear shift invariant system. So we did that. Okay, talked about that. Good. All right. So mathematically, this is probably the most essential equation in the entire course, right? Because all of MRI is based on this equation, right? So if you understand what is happening here, this relationship between this function, which is a set of amplitudes or brightnesses in space, and this function, which is in spatial frequency space, you will understand MR very well. This is called the Fourier transform, and it wound up, this continuous Fourier transform was developed after Fourier posited that when solving a particular differential equation, if one periodic function was a solution, and then another periodic function was another solution, he could add those two up and have a third solution, right? And that turned into discrete Fourier analysis, and he was solving the heat equation, which is a simple differential equation. And so he came up with this hypothesis that, if I have these, periodic functions across a certain domain, I can create any function in there that will be a solution, because all of these functions are a solution, right? Which, was a huge insight, right? And now in the continuous domain, you state that if I have a continuous function, in this case, it's a 2D function in the plane, I can figure out the frequency components in this function, those frequency components in this function, by performing this operation, this Fourier transform operation. And those frequency components are continuous, right? So this isn't discrete periodic functions. This is actually a set of continuous functions, right? Which, when you actually look at MR, like when you do a Fourier transform on a computer, by necessity, it is not a continuous Fourier transform. You have to sort of do a discrete Fourier transform in order to set it up digitally. But the theory is here. So let's just look at this equation and see if we can make sense out of it. This is easy, right? This is our object, somebody's face, somebody's brain, the actual underlying thing. We then multiply it by this function, and recall from, I guess we did this on Monday, right? That this function is what's called a phasor. So it has unit magnitude, and the only thing that happens is in the complex plane, it changes its phase, right? And it changes its phase as a function of whatever the number is in here. As this number gets bigger, the phase angle gets bigger, so it wraps around farther and farther, right? So I've got 4 variables in here. The 2 variables are spatial variables, and we're integrating across those. So they're just there to do the integral, right? These 2 numbers are parameters that show up over here. These are our, independent positions in Fourier space that we're evaluating. So we're getting a value here at a mu and a nu, right? And they show up here in the equation. And during this integral, those 2 values are fixed, right, for each integral. And the things that vary are x and y as we do the integral. So the function varies, the phasor varies as x and y changes value as we're performing the integral. And then for each mu and u value, we get a Fourier transform value, right? The inverse transform looks practically identical, except the phasor is rotating in the opposite direction. There's no negative sign here. So you can take the Fourier transform of f of x, perform the integral by, not doing a negative j here, but a positive, integrating in Fourier space over nu and u, and you'll come back to the original function. Right? This is called the duality of a Fourier transform. This sure looks like a Fourier transform, except for that negative sign there, right? I don't know why the negative sign is up here and not down here. I don't know why they're not swapped. Anybody know? I don't know. I mean, they could be swapped, right? I think. Yeah, so I don't know. This is like, well, positive. So that's a clockwise rotation, I guess. Okay, so there are whole books written on this transform. Bracewell has a very good book on the Fourier transform. I've put in the module in the materials there's a PDF of chapters of books that are on the Fourier transform. Okay, and so you should probably, if you're interested in imaging, you should probably read those chapters and really start working them out for yourself. Okay, where this becomes hard to say, this nu and mu, and you can't understand which one's which. It's better, we use a notation in MR called k-space, and instead of those mu and u variables, we use kx and ky. And these are called spatial frequencies. They're, units are cycles per centimeter, right? And it's just easier to deal with. We can thank, who wrote the medical physics paper on k-space? And it was like 1983 or something like that. It was I forget, but some guy decided, oh, here's a better notation for this whole business, and gave us k-space. So here we're going to do it in 1D, this Fourier transform. So here's our function g of x, multiply it by e to the minus j 2 pi kx x, and we're going to integrate over all x to get that done, right? We know from the Euler formula, from the mathematics most beautiful equation in the world, that we can break this function into a cosine part and a sine part with the j here, right? So this is equivalent to these 2 integrals, okay? Which now makes the integration sometimes easier. It makes, if this is an odd function, this is going to integrate to 0, etc. There's certain things that can happen. But in your undergrad calculus course, when you took a whole section on integrals of products, so we study integral of f times g, and you do all of those things. This is why you did it, right? Because it's showing up here, right? And it turns out that our right, that our g is one function and this is the other. So you can see what's going to happen with this integral. If you think about it for a second, we're integrating over all of space. X is our integration variable here. So if g matches cos 2 pi kx x as a function, as we're moving along in x, if g rides along with that function, the integral will obtain a high value, right? If on the other hand, it is in counter phase to this cosine, right? Let's say it's a sine wave with many cycles, it will average out to 0, right? So this term basically is saying, how much does this function look like this? How much cos 2 pi kx is x is in this function, right? Then the integral will have a high value and not 0. Similarly over here, sine is an odd function, goes through the origin. This is an even function, is 1 at the origin. So you basically have the same function, just shifted by pi by 2. So how much does g of x, its same function, look like sine, right? So the way we can, so let's ask the question, how much does this function look like a sine wave, right? And we perform that integral and we get values at different kx or different frequencies. In this case, we've substituted with omega. The kx is equal to omega. And say, well, what's the amplitude when we do the integral on this square wave with a sine wave at this frequency? And so here's our sine wave. We multiply it by this, do that integral, and we end up with some value. In this case, it's 4 over pi, right? And then we perform the integral again with a higher at a higher frequency, we change the k value, do the integral again, and we get another coefficient, which is 4 over 3 pi and 4 over 5 pi as the frequency goes up. So these amplitudes are getting smaller as the frequency is going up. And those amplitudes are the Fourier coefficients of this function, right? This periodic function. So when we add up using those amplitudes, a sine wave and then a sine wave with, 3 times the frequency, and then a sine wave with 5 times the frequency at this amplitude, this is what the sums look like until finally we do that many, many, many times and we get a square wave, right? Finally, we have frequencies that are almost infinitely high to produce these ridiculously sharp corners. But as we get to that higher and higher frequency, these coefficients get smaller and smaller and smaller, right? When Fourier first came up with this idea, this result produced great controversy, right? Because people could not believe that from a set of sine waves, you could build something that had sharp corners. Just mathematically, that just did not seem viable, right? And so there was a lot of pushback. Luckily, I guess he was an influential person and held his ground. Said, no, it really works, But this was thought by a lot of mathematicians to be proof that this is a crazy theory, right? That you could build something so sharp. So that's how you build functions from the Fourier components, right? If we wanted to find out if we go back to this transform and we ask, what are the frequency components of our function g of x? Then here, if g of x is this, square wave, we perform that transform and we'll get these values. These amplitudes are the things that come out, right? Often, if any of you have been in electrical engineering or in signals, most of the time when you first are introduced to the Fourier transform, it's in time domain signals, right? Because you're trying to figure out, you've got some voltage versus time, and you want to know, how do I filter it such that I get rid of spike noise, or how do I determine what the different coefficients are in this, or I'm looking for a certain signature inside a random a noisy signal. So I take the transform and I look for peaks that are characteristic of some underlying process that I'm interested in. Another thing is, like, if you play a note on a violin and you record it, you get a function which is voltage versus time from your amplifier and your microphone, right? So you record that signal and you get some waveform. And then you record a cello, right? And it looks similar, that, voltage versus time for your microphone. But when you take the Fourier transform, you will get spectra that say, that's a violin, that's a cello. It'll have a fingerprint that says, why you as a human can distinguish the difference between those two things. Somehow you are doing frequency analysis, right? And relative amounts of different frequencies turn out to be a violin or a cello, or your mother's voice or your grandmother's voice, right? So you're really good. Your brain is super tuned to voices. Like, you can tell people's voices, like, just with a small sample, right? And so our brains are really good at that. Our brains spatially, when we look at spatial information, our brains are really good at faces. You can instantly sort of recognize people and stuff like that. You might have only seen that person twice in your life, but bang, for whatever process is going on, it goes whoop and says, I've seen that person before, right? And so it's probably using, spatial frequencies and some kind of neural convolution. Yeah.
Neurons in human beings' brain is much larger than even the current best machine learning algorithms.
Oh yeah. So the comment is that the brain, if you look at deep learning and you say, well, how many neurons are connected in a large network, and then you look at the brain, it is a lot more. I mean, you've got billions of neurons, right? And they're not all connected, but they're in, different pathways. I'm sure they're more highly connected, more than likely more highly connected than what we create on computers. Although I don't know. I mean, I have no idea, about the depth of the connections, just how broad those are. Do you know, Tom? Is there any? Yeah. Yeah. But if you looked at a neuron and asked, how many other neurons are affected when I fire? Is it like thousands, millions? I just don't even know that. Yeah, it's probably downstream effects in the millions, probably. Yeah. That's a good project, right? So this is like what's that? Camille Ergerbil has that brain grant or whatever. They're mapping these connectome. Yeah. So, well, we'll read up on it and see what answer they get. But it's big. It's also has really good redundancies, right? So if you damage part of it, it can work around the damage pretty well. And one thing that is really cool is they took, I think she was like the 4th best chess player in the world or something, And they did an fMRI when she was looking at chest positions. They would just put up a position and say, okay, you're white, or whatever. And they would look at, using functional MR, which regions of her brain were lighting up when this happened, right? And it turned out she somehow had co-opted the region that recognizes faces, right? So that thing was lighting up. So basically they looked like things she knew of the faces, and she goes, oh boy, that's a scary face, or whatever. So it's pretty cool. And that you'll learn about fMRI. fMRI it's fantastic. It's a really neat field. Okay, what are we doing here? So that's time. Okay, so how do you know it's a violin and not a cello? And then spatial, that's what we're doing, which are pictures, sort of functions of brightness as a function of position, usually in X and Y. X and Y makes a lot of sense because your visual system, even though you have depth cues, right? Because you have two eyes, there's a lot of depth cueing going on. But when you look at a 2D picture on the wall, it's 2D, right? So that's a 2D function, right? And so you have brightness as a function of X and Y. Computing Fourier transforms, I encourage you to sit down with these and understand like why these are true, in that the Fourier transform of a delta function. So now I have a function that's all zeros, and then it's some very spiky thing, and then it goes back down and it's all zeros again. And I ask, well, what's the Fourier transform of that? How many frequencies do I need to produce that thing? What is that in audio? What's a delta function in audio? What would it sound like? Anybody just take a guess? Wouldn't sound like Pavarotti, right? It's silent. It's silent, silent, silent. Then for an extraordinarily brief time, it is not silent. And then it's silent, silent, silent. So what's that? It's like a pop, right? It's like if you're listening to a record and there's some fault on the record and it goes pop, right? That's like a delta function, right? And what do you think the frequency components of that function are? Are they low frequencies? Like just what are low frequencies in audio? They're like the bass, right? I got these new speakers and I didn't even know, like, it turns out modern music, like modern hip hop and stuff, there are frequencies in there I never knew existed, right? I got these new speakers and it's just like, the whole house is like going at this really low frequency. So now when you ask, okay, what is the frequency components of a pop that comes through my system? There's a lot of frequencies, right? It's high frequencies, right? Because it's like a ping sound, very loud, really, really loud, right? So that mathematically is described right here. You take the Fourier transform of the delta function, which is the pop that came out of our time domain signal. And when we take the Fourier transform of that with that integral, because this thing only exists, right, at x equals 0, it sifts out every time we pass for whatever value of k. It doesn't matter. I can put any value of kx here. When this integral is flying by with, x equals 0, this is the only time this is non-zero. So regardless of what frequency I put here, right, I get 1, right? So that means for every darn frequency, from kx from minus infinity to infinity, I get 1. So that says every frequency is represented in that spike, right? So it's a hugely broad thing. And that's why in reality, when your speaker makes the pop, it can't make every frequency, and your ears can't hear every frequency. So it rolls off and you hear a pop with a slight thud, right? Because it's like, it's it's muted somehow. But that's a delta function. Its Fourier coefficients, the number of frequencies in there, it's infinite. Okay. Never actually happens. If you have a delta function offset from the origin, so at this delta function here is only non-zero when x equals x naught. So it's some place off, x naught represents some place off of 0. You just replace that in your as your function here, and it turns out the thing that gets sifted out, regardless of the value of kx, is this. It's kx times x naught, right? Because this becomes non-zero at x equals x naught, so it sifts this out. So that means that as kx changes for different values of kx, depending on x naught, I will have different values of this function. And so this thing is a cycloid, basically. It's just a phasor that is going around with this frequency, right? As a function of different values of kx, it's going around at 2 pi x naught, right? That's its frequency. We'll look at a diagram of that. Fourier transform of, and this is our rectangle function. We recall the rectangle function, we'll look at a diagram of that too, is 0 up until 1/2, and then 0 after 1/2. So I can just integrate it between those two values. It's 1 here, so though I put a 1 right here, that's my function I'm putting into the Fourier transform. And when you figure out how to do this finite integral, which I leave to you as an exercise, this is the equation you get, right, from that finite integral, is this one here. And this, when you rearrange it, becomes, using Euler's theorem again, right, becomes sine of pi kx over pi kx. And so it's our sinc function, right? It oscillates like a sine wave. It decays like 1 over x or 1 over kx. And we call that a sinc function. So here's our, in audio, our pop, right? And it has all these frequencies in it, right? In space, it's our delta function, right? Which ideally, like in the CT example, is a spot that is so small, it's much smaller than all the detector elements and things like that in the system, so it's delta function. So to image it accurately, you need to image out to very high frequencies. Our system will not achieve that, right? That's why we can measure how it falls off with our system, right? It's because it doesn't have these frequencies out here. And then when I shift off the axis, right, we get a function that as a function of kx. So here's kx on this axis here. Regardless of what kx is, this is 1. Here, as I change kx, my phase of this signal changes, right? And the rate at which it changes is dependent on x naught. As x naught gets bigger, this rate of spiraling as a function of position in kx will get higher. It'll wind up higher. Okay. Here's the Fourier transform of the rectangle. When we work it out, we get this function. So it's sine x over x. And it looks like that. This is you can see why this is a really important function, right? Being the Fourier transform of a rectangle. Right? Sometimes called a sombrero function. Right? Okay, I'll leave this for you to do, like plug these into the equation for the Fourier transform. Okay, go back to here, this, okay? Here's the fundamental Fourier transform. In 1D, you just have to wipe out the y, right? Here it is in 1D. So plug it into this equation, right? These functions. And just sort of get used to why, if I plug this in and take its Fourier transform, why do I get a delta function that it, is zero everywhere except kx equals k naught, right? Similarly, and this is kind of interesting, when I have a cosine function, which recall a cosine function is an even function. It has the value of 1 at 0, and then as we go both positive and negative, it goes through the same values, right, away. And this function is oscillating at this frequency, 2 pi k sub 0 in space, so it's oscillating at that frequency, right? When I take its Fourier transform, I get a symmetric function in the sense that I get a delta function at kx equals minus k naught, or at k naught, and I get a delta function at kx equals minus k naught. So I get two spikes separated, they're symmetric about the origin, okay? And for sine, again, I get two spikes, however, they're phase shifted such that they're imaginary, right? So to do these, you can remember the rule that cos, is the real part of e to the ix, which looks like that, right? We've already looked at linearity, and the Fourier transform as an operator or as a system is a linear operator, linear function. So if I have a function that I'm going to take the Fourier transform on that looks like this, it's the sum of two functions. And those, I have indices here, A of gx, B of h. Then I can take the Fourier transform of the G of G, put it over here, that's G kx. Take the Fourier transform of H independently, not even looking at G, put it right here, that's Fourier transform of H. And then the A just is multiplied by the transform, and the B is multiplied by the transform. So that's the linear, that's because it's linear. And that works in 2D as well, right? So this becomes very useful, and this is called duality. We already kind of looked at this in that the Fourier transform of the Fourier transform of something is related to that thing. Okay, so if I take the Fourier transform of G, this function here, so here's my little g x, right? And I get this function in the space kx. In that space, if I take the Fourier transform of this function, right? So let's do that down here. So now I've got this thing. I've put x in here instead of kx, but it's just a function as, a function of an independent variable. Take the Fourier transform of that thing. I get my original function back, but it's flipped around the origin. Okay, so fascinating, right? So that if the function's symmetric, like a Gaussian or something like that, I take its Fourier transform, I get another function, take the Fourier transform of that, I get my same function back, right? If it's symmetric, right? That's called duality. And moving between Fourier space and space with a few, if you know a few Fourier transforms in your head, with that and the convolution theorem, you can build almost anything, right? You know pretty well anything that can happen. Okay, here's an application of duality. If we say, what is the Fourier transform of sinc x, right? I know I can write down this equation, sine, pi x over pi x, put it into the Fourier transform formula. So here's my argument, and then run this integral. Well, this looks like a kind of a complicated integral, right? So it might be hard, actually, when you're doing integration. I have, basically 3 functions like sine 1 over x and this darn thing, right? And I want to do an integral of that over, which is indefinite. But what I just told you should tell you what the Fourier transform is of sinc, right? Because how did we get the sinc function? Right? We took the Fourier transform of a rectangle, right? So that's a symmetric function. Sinc's a symmetric function. So what's the Fourier transform of sinc? It's our rectangle function, right? You just go back and forth, right? So working in either domain, right? You basically can, using this duality, can figure out what Fourier transforms are for many functions, right? So here, officially, the Fourier transform of the sinc function is, the rectangle function with the argument flipped. But for the rect function, it doesn't matter that you flip the argument. It's the same function. So here's a set of transform pairs. And this, in one of those books, the PDF of the chapters I gave you, has a pictorial sort of little library of Fourier transforms. So you have a picture of a transform over here, right? And it's dual, right? It's pair. So you basically want that set of pictures in your head all the time. There's some key Fourier transforms you got to know, right? Here's a few of them. Fourier transform of 1, right? We know what that is. So if I have an image that is just a constant value everywhere, it's just a gray background and there's no variation, right? So it's 1 everywhere. What's its Fourier transform? It's a spike. It's a delta function, right? And it turns out it's kind of like it'll be a DC. It just says, only thing you have in this image is an offset, like a DC offset, and it shows you a spike at the origin, at no spatial frequency. It's just at the DC point, right? So it's the spatial frequency 0, often called DC, like, DC offset. We know from experience, we've already done it, that the Fourier transform of the delta function is a constant. It's 1, and that's the dual, which is nice. Offset that delta function in 2 dimensions, we get this function, which is a plane wave, right? So if I have a delta function, I offset from the origin, and I look in the Fourier space, that turns out to not be a constant. It's a sine wave, but it's a plane wave, and it's related obviously to where I put that delta function offset. The direction of the plane wave will change depending on where I put that offset. This is an exceedingly useful function, and as we'll see maybe today. What are we at? I don't know. It's called a sampling comb. And it's a continuous function in x and y, and it's 0 everywhere except at these locations, at 0 and then 1 delta x, 2 delta x, 3 delta x, right? So it's a sampling comb. And it turns out the Fourier transform as a sampling comb is a sampling comb, right? Which for a moment there, you're like, what? Didn't we know? Those are delta functions. Shouldn't they all be, DC? But in a sampling comb, remember, you've got a whole bunch of displaced delta functions. So there's sine waves and stuff in there. So it turns out when you add all that up, you get another sampling comb in the Fourier space. So we'll look at a picture of that. A plane wave is a delta function and an offset. Here are the Fourier transform sine and cos we already looked at. Rect we looked at. Think we looked at. Comb, we sort of looked at that. And this one is very useful. This is the Fourier transform of a blob, which has the form of a Gaussian. So if it's got a central peak and then it rolls off as, x e to the minus x squared, y squared, etc. So this is like e to the minus pi r squared kind of thing. And its Fourier transform is itself, right? we'll see how it scales, but a Gaussian goes to a Gaussian is the way to remember that, right? These are all in the Prince links book, so you don't have to write them down, but you should go through the list and at least understand slightly why these are true. Let's look at some properties. If we have this function f is Fourier transforms cap f, little g, cap g, okay? We did linearity already. We know that's true. We know what translation is. We did that. You multiply by this plane wave. The conjugate is interesting. So if I take the complex conjugate of fxy, you just take the complex conjugate of the transform, but you reflect around the origin, okay, to get the Fourier transform because there's negatives here. If this is real valued, then this thing is conjugate symmetric, it's called. So if you look at a location in Fourier space mu v, then when you flip around to around the origin to minus mu minus v, you get the complex conjugate of what the value is here. And that is if this is a real valued function. Okay, so the phase is 0 everywhere. It's just a real valued function. Similarly, you can imagine that when you take the Fourier transform of a function that has this property, right, that it is conjugate symmetric, you will get a real valued function as the Fourier transform. This turns out to be important in MR because the phase map of the Fourier transform holds most of the information about what's going on in MR. Signal reversing, that just, if this is your Fourier or your function, you just do the same thing with Fourier transform. Same with rotation. If I have a function and I rotate it, take the Fourier transform of that thing, it basically is just the Fourier transform of the original rotated, so it'll just do the same rotation. That kind of makes sense. Here's this scaling is, as we looked at that Gaussian, remember? So if I have a Fourier transform and I scale my axes by some factor, when I look at what happens in the Fourier space, I scale it by the inverse of that factor, and I have to normalize also by the amount of scaling. So if, for example, I look at a Gaussian and in space, I make the Gaussian wider, right, by essentially the appropriate value of A here, then in the Fourier space, what will happen is the transform will get narrower as in the Fourier space. And that kind of makes sense if you think of the delta function. So if I go narrow, 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 I get ultimately super wide in frequency space, right? And then as my function gets wider, 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 wider in space, I get many more lower frequencies in space. And in the Fourier domain, it gets narrower, 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 such that most of my power is at low frequencies. This is the big one. F convolved with G. This is a huge thing. So if I have some function F and I have one of my little convolution kernels that I was going to convolve my F with, swing, 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 right? If I take the Fourier transform of F and I take the Fourier transform of G, all I do is multiply those two functions together in Fourier space. And that's the Fourier transform of F convolved with G. Wow, that is cool, right? That's a huge time saving for doing lots of stuff, right? So if I have a function and I'm going to do a convolution of that function, oftentimes it's way quicker to take the Fourier transform of both those functions, do this multiplication, bump, that's one multiplication point by point, right? Take the inverse Fourier transform of that thing and go back to the result for this. Okay, so this is a huge deal, this function here. And when you're understanding artifacts in magnetic resonance, the ability to flip between these two spaces is very important. So if this is my raw data space and I say, oh, my raw data got corrupted, can I describe that corruption of the raw data in terms of a multiplication by some function? If I can, then I pretty well know what's going to happen with my image, because it's just, going to be the convolution of whatever the description of that corruption is. So if I have the Fourier transform of my object with many, many high frequencies, and then for whatever reason, I can only sample a very small region of that Fourier space, I can model that as multiplication by some window. It's zeros everywhere and non-zero, like a rectangle or something. And then I know what will happen to my image. It'll be convolved with Fourier transform, the inverse Fourier transform of that window. Okay. And similarly, I mean, it goes both ways, right? The product in space is the convolution of the Fourier transforms. And then this relationship here tells us that if I have a function in space and it's varying and it has various amplitudes, and I ask, when I take the Fourier transform, how much stuff am I going to get in the Fourier transform? How much non-zero stuff will be over there, right? It turns out that if you take all of the magnitudes of your function, it can be a complex function. So we'll look at the magnitude at each point, square it, integrate that whole function. So now I have this positive function. I take the integral under the whole thing, right? It turns out to be identical to the value of the integral of the Fourier transform components, magnitude integrated. And so this is called Parseval's theorem. It's a way of saying power is conserved. If I have signal power in the spatial domain, I will have signal power in the Fourier domain, right? It can't magically be zero over there if I got signal power over here. And so this can be used to test certain hypotheses, and you can say, well, I think this is how it's going, and you look at it and you say, yeah, but the equations you've got here would not, submit to Parseval's theorem. You'd get more energy over here than over here. So it's a good check of whether or not you're using the right math. Okay, what are we at? Oh, I'm gonna quit there. That's probably enough. And we're putting together another problem set, which Tom will be due not this Friday, but next Friday. It'll be, and I'll try and get it posted up today. Okay, this evening. All right. Any questions? Everybody got? You can stick around and I'll answer.
Thank you.